So we start with intro to stream ciphers. So where are we? Just give you a little bit the big picture. Where are we in this world of the universe of cryptography? We had the similar picture in the beginning. When we talk about cryptography, there are three branches. There is symmetric cryptography, there's asymmetric cryptography or public key cryptography, and there are protocols, okay? And you might vaguely remember the first time we met 2 weeks ago, I told you the timeline is from left to right, so we start with symmetric ones. And what I want to introduce now is a further classification, the two flavors, two families of symmetric crypto algorithms, symmetric ciphers, namely stream ciphers and block ciphers, okay? So, and we do 2 weeks of stream ciphers, starting today, and then there will be roughly 4 weeks of block ciphers, okay? But where we are now is here, okay? That's today. So we start with stream ciphers, okay? We'll switch to okay, so let's give a brief motivation. Now I have a question to ask. Who of you has a cell phone, a mobile phone? Who? That's Generation X, right? This is so crazy. I got my first cell phone when I was, 39. So times have changed. So surprise, surprise, they're based on the GSM standard. Have you heard that? GSM, that's the GSM cell phone. And GSM exists since the mid-1980s, and GSM was the first big application of cryptography in consumer products, okay, because it's voice encryption. If you talk on your cell phone, what's happening is this is my really cheap Motorola cell phone, which is completely outdated here, right? So what happens if, before I called our team assistant and I said, we're out of chalk is Kreide. And, Irmgard Kühn just brought that down. So what's happening is I'm not directly connecting to my office up in this building. What happened is you get actually a connection to the base station, to the cell tower, which is somewhere on campus, okay? So, and then you get your connection between those two. This is Airlinks. This is really the mobile link, and after this it goes back into the backbone regular phone system. So, however, the voice is digitally being transmitted. It's not an analog signal. It's a digital communication link, and this is being encrypted with a stream cipher, okay? So what's happening here is my voice message I call X, that's a ciphertext here, is being encrypted with some kind of crypto algorithm. It gives the ciphertext Y. Y, encrypted stuff, is actually going through the Airlink. There's somewhere probably in the Audimax or so, there's probably a cell tower here on campus at Ruhr-Uni. But it's the voice messages, the quantized voice is not sending in plain, in clear text. It's being encrypted as a ciphertext Y. On the receiver side, that means in the cell tower decrypts the signal, recovers my voice signal, and feeds it into the regular phone system, okay? So this is mobile security in 60 seconds, okay? So this is very roughly how that works. Now, how is that related to our lecture today? The encryption and decryption operation is done with a stream cipher, okay? And I'm going to explain to you in 1 second what the stream cipher is. I would like to ask you, leave about 10 Kästchen, 10 little squares free underneath. In about 10 minutes, we're going to extend this drawing here. So you need about 10 little squares. You know what I'm talking about? So if you don't start writing here, start writing here, okay? Then you get a nicer lecture notes. Okay, so so you might ask yourself, what is a stream cipher? And I think it's a very beautiful name because it's self-explanatory. So it has to do with streaming bits, so you don't. Hello, hey. Hello. Yeah. They're called stream cipher because they process one bit after another. So we have this picture of bits of a message, of a voice message or file, streaming in, flowing, you know, strömen, the German word strömen, to stream, you know, so, and that means we encrypt stream cipher. What the definition is, a stream cipher encrypts bits individually. That means one bit by one bit. Individually. As opposed to, you know, you see up there block ciphers, and how do block ciphers operate? Surprise, surprise, they take blocks of bits. You know, and nowadays most algorithms take 128 bits, so 16 bytes of data, and you encrypt, in one encryption operation, you process 128 bits of plain text, and stream cipher only processes one bit, you know, processing, and then the second bit, processing, third bit, processing. You got the idea, very simple. Conceptually, they're very simple, okay? So the question is, how does the encryption work here? And now, and there's something strange about stream ciphers, because the encryption and decryption by itself are very, 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 very simple, extremely simple, okay? So immediately, remember we did the Caesar cipher and then the affine cipher, and we do exactly the same. You know, that is going to be a red box, the definition. The encryption operation computes plain text bits, and because they're bits, you know, they're called yi, so that will be y1, y2, y3, so that gets the index y. Of course, operating on the plain text, what happens is you take your plain text bit xy, you know, the first bit, for instance, of my voice signal, and you add something like the key, you know, except the key in stream ciphers we call S, we don't call K, and we will, towards the end of the lecture, you will see why. And you add that modulo 2, okay? This is encryption, okay? Now we do decryption. Decryption looks very, very similar. You take your ciphertext, you get from the air link, you know, that's now the cell tower, right? The cell tower. The cell tower takes the bit it gets through the air link. Surprisingly, also adds, you know, addieren the key bit SI, modulo 2, and that's it. So what we're going to do for half an hour or so today, we're going to talk about these equations, okay? My first question is these equations, they're similar to equations we had last Thursday, right? Which cipher had almost the same equation here? Which algorithm? We only had two algorithms last week, so there's A and B. Which one? Any volunteers here? There must have been a homework assignment here. That looks very similar to the shift cipher. Very good. This is a shift cipher. Except we didn't. What's the big difference? The shift cipher was mod 26. This is mod 2. Okay. So now we want to discuss stuff. Okay. And what's also scary, this ends up to be fairly secure, the system. The shift cipher was not. So we're going to have a long discussion today, okay, about this orange box here, okay? So the first question that we have, what would we expect at this point here? What would we expect instead of a plus sign here, instead of the addition sign? What should that be? A minus, right? Isn't it? I mean, here we add the key bit to y, so we would expect that we subtract the key bit. So that's the first question is, why are decryption and encryption the same operation? Question mark. And now we play a little bit with that. So we start with the, so what we mainly have to show is that this works out, right? If you decrypt something, you actually get the plain text out again. And let's concentrate on the second equation. Or let's start with the second equation. Okay, so we start with the decryption. And what is the decryption operation? Well, as you can see there, we take our ciphertext and we add the SI, the key bit, right? The SI is something like the key bit, okay? Now we go one equation up. We have a look at here. How is this yi computed? Well, the yi is computed as xi plus si. It's just your substitute for yi, you substitute the encryption equation. So and this, of course, can be rewritten as xi plus, this is si plus si, it's 2si. Okay. But the whole equation is taken, is computed, evaluated modulo 2. But what is 2 modulo 2? What happens if you divide 2 by 2? What is the remainder? 0. That means this 2si is always 0. Okay? So this is xi. Okay? That's a proof that encryption and decryption are the same operation. Maybe a remark at this point here is xi, yi, and si are in Z2, in this integer ring 2. That means this is a very, very fancy way of saying the bits. Okay, very fancy way of saying bits is calling that Z2, right? So we have the arithmetic rules in Z2. So that's the this is QED here. It's the end of the proof. That means encryption, decryption is the same operation. And maybe let's write that down because this is a very important thing to know in cryptography. So here from this follows mod 2 addition and subtraction are the same operation. So it doesn't matter whether you add a value modulo 2 or you subtract a value modulo 2. These are the same operations. Because here, of course, at this point, here, where are we? Here, at this point. You can also put a minus sign and you get the right result. Of course, you can take yi and subtract the si and you get the right result out. Of course, you can do that. The only thing we showed here at this point is you can also add. So addition and subtraction are the same operation, modulo 2, and this is coming up all the time for the rest of your life now. Okay, if you stay in cryptography, there's always modulo 2 arithmetic, and very often we have to subtract, but we just write addition because it's more convenient to write. Okay. So with this knowledge, so here we just showed that this equation is true. We can become a little bit more technical here. What's happening here in this encryption function? And again, you should leave a little bit space here underneath again. So what we have here, we have voice bits, x1, x2, x3. Somehow my voice is being turned into a digital signal, into bits. There are ways of doing that, right? You have to quantification in time and in amplitude, right? So my voice is going to be a series of bits, bit x1, bit x2, bit x3. Now the encryption is a simple modulo 2 addition, and there's a special symbol for that, namely it's simply a plus symbol with a circle. This means modulo 2, okay? Modulo 2 addition, of course. So what do we add? Well, we take my voice bits and we add this key stream, something like the key, SI here. So here you add S1, S2, S3, and so forth. On the receiving side, you do the same. You take Y1, you add S1 to it. Okay. So you have S1, S2, S3, and so forth. And your result is again x1, x2. And here in the middle of the channel, we have the sequence of yi. Okay. So this is very roughly, on a high level, what's happening in your cell phone. This is how your cell phone operates, right? Your cell phone does this modulo 2 addition for each voice bit. On the receiving side, the cell tower somewhere hidden on campus, the same thing happens. It takes the encrypted bits, again, the same sequence is being added, and you get the original result out. And there are a lot of open questions, and we're going to discuss them today. Okay, so let's have a closer let's look a little bit closer at the modulo 2 addition. This is going to be super, super important, not only for stream ciphers. Again, this is going to haunt you if you do cryptography. Modulo 2 addition comes up all the time, okay? And what we do now is a very little thing, takes us 2 minutes, but it's very important for understanding modern cryptography. What I'm going to show, if you have a sleep, if you whatever, work on your math assignment, stop it now, okay? Pay attention, the next 120 seconds are going to be very important in your life. So what we want to do is, we want to look at what's happening here in the cell phone, what's happening in my Motorola phone here, okay? So we do modulo 2 addition. There aren't that many possible values for x, and there aren't that many possible values for s, and we simply want to tabulate all of them. So we take xi, we take si. There's only si is a bit, so here we only get the values 0 and 1. The same holds for si. So we've seen that, right? They're called truth tables, right? So we do a little truth table. And here is the result, the ciphertext that we compute, yi, which is xi plus si mod 2. So we do modulo 2 addition here. 0 plus 0 is 0, very good. 0 plus 1 modulo 2 is 1. 1 plus 0. That's now the last line is the only time where we have to wake up and pay attention. 1 plus 1 modulo 2 is very good. Okay, so that's a little truth table. We're almost through, okay? Then you can go back to sleep, okay? So we look at that, and now this is, mod 2 operation. But if you look at that from an electrical engineering point of view, and show my colleagues here this truth table, they wouldn't say this is modulo 2. They say, well, that's a truth table of a gate, right? Digital gate, a binary gate. And what kind of gate is that here? Yeah, very good. This is the XOR gate. Okay, and now lesson learned, buckle up, it's very exciting now. Modulo 2 addition is the same as XOR. You can go back to sleep. That was the Erkenntnis for today, okay? So it's very, very important. Mod 2 addition is the same as the XOR operation. What I sometimes say half jokingly is, the theoretical cryptographer or the crypto person looks at that and says this is a modulo 2 addition, and the engineer or the applied crypto person looks and then says this is an XOR, but these are just two different names for the same thing, right? Whether you call that an XOR or modulo 2 addition, these are the same operation, they get the same result, okay? And this symbol, is it's mod 2 or XOR, and it's going to be very, very, very important. And now, let's stay a little bit with this XOR gate, because it's why the XOR gate? Why not the NAND gate or something else, or AND gate or NOR gate? They're pretty nice properties of that. Let's assume you're the good guy, you're Alice, you want to encrypt. So you're Alice, or you're my cell phone, okay? You're inside my cell phone. So you want to encrypt, and I ask you, please, Mr. Cell Phone or Miss Cell Phone, please encrypt my bit 0. Okay, so I give you the bit 0, and now somehow the cell phone has to generate this key bit as 1. And that's going to be very important where this bit is coming from. But right now, we only know it can be either 0 or 1. And now it's interesting, if you encrypt the 0, if the key bit is 0, then the ciphertext is 0. If the key bit is 1, outcome is 1. That means the 0 can be encrypted as either a 0 or 1, okay, which is good. Would be bad if you encrypt a 0, if 90% of the time a plaintext 0 would end up being a ciphertext 0. You know what I'm saying? So and if this, if you have a 50-50 chance that this is either 0 or 1, and if this is somehow random, we're going to talk about randomness today, then this is probably looks like a reasonable encryption function. Same goes here. What happens if your plaintext is a 1? If you want to encrypt the value 1, depending on your key bit here, if the key bit is a 0, this turns into a 1. If the key bit is a 1, it turns into a 0. Same story. That means each plaintext bit can either become a 0 or a 1. Okay? So that's kind of an interesting thing. What is also interesting, this is one discussion. Okay, the other discussion we can have about the XOR function or the mod 2 addition is, what I did so far, I fixed the plaintext and I looked at the ciphertext bit. Now let's do the other way around. Let's look at the situation where we fix SI. So, and first we look at the cases where the key bit is 0. Okay, and again, you have to wake up here. I should have told you. Okay, this is very important. This is very easy, but very important for life as a cryptographer. So I want to discuss what's happening when the key bit is 0. Here, the SI, the key stream bit or the key bit is 0. What happens? Well, the 0 plus 0 is 0. 1 plus 0 is 1. So what happens with the plaintext bit if the key bit is 0 here? Stays the same. It's not changed, right? Everybody with me? Right. 0 becomes a 0, 1 becomes a 1. Okay? Case number 1. There's only one other case, obviously, namely the case that we XOR a 1 from the top, right? SI is coming from the top. Okay? So what's happening? Your plaintext is 0, you XOR a 1, you get a 1 out. That means the 0 is flipped. Okay? Everybody with me? What's happening here? You have a 1, you add a 1, the 1 becomes a 0. So it's flipped again. So the rule is, if you XOR with a 0, the bit goes through unchanged. If you XOR 1, you have a bit flip in both cases, in the 0 case and the 1 case. Everybody with me? So it's only, if the key bit is 0, the plain text path is unchanged. If the key bit is 1, you flip, okay? And now comes a very, very nice unmathematical interpretation of this operation, okay? We only look at the key bits at this point, okay? Let's say Hauptfall 1, case number 1, key bit is 0, S1 is 0, S1 is 0 here. So what's happening with X1? Well, X1 is XORed with 0, stays X1, right? Same value. You add a 0 again, you get the original X1 out. Everybody with me? Because there was no change here, no change here. This was orange, orange, right? Now the other case is this value, this bit has the value 1. That means you add a 1 here, you add a 1 here. So what's happening is X1 gets in, gets flipped, right? Either from 0 to 1 or from 1 to 0, no matter, but it's going to be flipped. These are the two blue cases here, right? Either the 0 becomes a 1 or the 1 becomes a 0. So you have a bit flip here. The flip bit, travels on the airwaves to the cell tower. What's happening here? It's flipped again, right? So you have two flips. That means if you encrypt a 0, what's happening is 0 becomes a 1, the 1 becomes a 0 again. So you have original value. The other possibility is you have a 1 here, means the 1 is flipped into a 0, and at the end, at the arrival point, the 0 is turned into a 1. That's nice, right? Isn't it? It's no modular arithmetic, it's just looking at the XOR, and it's very nice that a stream cipher has this simple way of operating. Okay, so very good. Do we have one? No, we don't have a blackboard free, so now we start with the Grau ist alle Theorie, right? Gray, all theory is gray. Let's look at a very simple example. Encryption of the ASCII letter, the ASCII code, so we want to encrypt the ASCII letter A. Now we look in, does anyone know what the ASCII table is? It's like an encoding, computer coding rule how characters are being encoded. And the ASCII A happens to be encoded as the value 65 this year. 1, 5 zeros, and a 1, 7 bits. That's the, right? 65 is the A, I think. Yeah. Okay. Going back to our diagram here. So we're talking about the first 7 bits here. Now what happens is you add the keystream bits, and we don't know what the keystream bits is. For now, we just assume. We just assume 7 bits, random bits in quotation mark. So I just assume random bits. So this is what I took from an example here: 0, 1, 0, 1, and then 1, 0, 1. Okay? Are you with me? Again, if you have to pay attention. They're not coming from anywhere particular. You can take any bit sequence that you want. Okay, right now we have not discussed where those bits are coming from, the keystream bits. I just gave them to you. Okay, so what's happening here is, well, they added modulo 2. So let's do a modulo 2 addition here. And now you do that bit by bit. 1 plus 1, modulo 2 is 0. 0 and 0 is 0. 0 and 1 is 1. 1, 0, 1, and 1. Is that right? Yup. Okay, and this is our ciphertext, Y1 up to Y7. Okay? So this is what your cell phone does for encryption, and then your cell phone sends this bit stream over. This is Y1 up to Y7. What happens on the receiving side? What does the cell tower does? What does the cell tower do? The cell tower takes those bits here, adds the keystream bit again. So again, if you want to write that nicely, you write, oh, I'm sorry. Pedagogically, I missed something. So what is a ciphertext? So, as an attacker, the attacker would see those bits here, 0, 0, 1, 1, 0, 1. The attacker would look in the ASCII table, and it turns out to be that this is the ASCII letter L, lowercase l, kleines l. Okay? So not the uppercase A anymore. This is the encryption with the stream cipher. It takes this, turns this uppercase A into a lowercase l. Now the cell tower receives the sequence 1101100, again, which is our sequence yi. The cell tower adds the same key sequence, right? You have to add S1 through S7 to it. So that means you have to add 0, 1. I'm just copying the sequence here. 0, 1. 101. And now the cell tower does module 2 addition, and this is your chance to do it, okay? You get 60 seconds to do this addition here, module 2, okay? I'll stop I take a break for 1 minute. Try to do that exercise. This is xi. So who got that correct result here? The big thing is, I don't know whether this is clear, the big surprising thing, the big Erkenntnis here should be that this xi is the same that we used here on the sending side, right? That means the receiver recovered the original ciphertext, okay? So this is, again, uppercase A. So this is the whole stuff we said before. You do 2 XORs with the same value. If you XOR a specific value as I here, and here you get the original message out. You recover the original bit. Okay, so this is working. Okay. So if you really paid attention, and if you're a creative thinker, by now you would think, this is almost too easy to be true, right? I mean, what we discussed so far is a stupid XOR gate, right? We said, you do an XOR here and an XOR there, and that's it. And you do cell phone encryption. And you can also do email encryption. You can do all kind of stuff. You said, there's something missing. We half an hour, we're done with stream ciphers, right? And the big thing that's missing, where I really made things look easier than they are, is the big question is now, where do we get the SIs from? Okay? I wasn't lying, but I kind of played them down. I just said, they come from somewhere. It turns out stream ciphers, so if we did so far, this is the easy part. The hard part is generating the SIs. How do we get the SIs? Okay, so big question at this point is how do we generate the key stream bits SI question mark. Maybe how do we start? Okay, let's start with this. Do you think it's a good idea to have something very nice regular, such as 0011, 0011, 0011? Who thinks that this is a stupid idea to do? I hope all arms, yeah, all arms. If it would be something nice and regular, such as 001100, an attacker Oscar, at this point on the channel, would do the same thing, right? It would, Oscar would also use 00110011 and recover the plain text. Okay, that doesn't work very nicely. So somehow I'm looking for an adjective, ein Wie-Wort, yeah, Adjektiv. What property should this sequence have? S1, S2, S3, they should be, what is the word in German? Yeah. No, not modular, no. Random, very good. Zufällig, random, okay. Somehow related to randomness. Yeah. So the SI should, has something to do with randomness. And what we want to do at this point now, we want to talk about random numbers a little bit, which brings us to the second part of the lecture today, random numbers. Chapter 2. And to be exact, we're not interested in random numbers per se. I guess we are, but I think from a functional point, we're interested in random number generators, how to generate them, okay, how to make them. So that's why I call that random number generators. And it's commonly abbreviated as RNGs, RNGs, random number generators. Zufallszahlengenerator in German. Okay, so, it's a big topic, and this is not an introduction to statistics. So what we mainly want to do, I want to show you the three families, the three types, three families of random number generators that we have. So we distinguish, das heißt, wir unterscheiden, we distinguish between three types of RNGs, okay? Type A is true random number generators, or TRNGs. So this is a very, very common abbreviation that you see. TRNG in the technical, applied technical crypto literature, and what they mean is true random number generators. There's a very good example for true random number generators is the €2 coin. Okay, if I take the €2 coin and I flip that, and that's a 1, and that's a 1. That's a 0, and we can do that 100 times, for instance, right? This is a very slow true random number generator, okay? And it works with the €1 coin and the 50-cent coin and, whatever, mark and dollars and cent and kronen and, whatever currency you want. So, so it works with the coins, it works with dice, Würfel, it works with the roulette table, it works with a lot of other things, okay? Generally speaking, TRNGs, these are true random numbers stem from random physical processes. Okay. E.g., zum Beispiel, what are examples? One I gave a few already. So one is coin flipping. Münzwurf, right? Coin is Münze and flipping is Wurf or drehen. Any other ideas? Maybe more computerish? You know, it's hard on a laptop to have somebody, you know, built in the laptop that flip coins for you, right? This is a pain in the neck. Any other ideas? What are random processes? What can we use for getting random bits? What's that? Lottery is good, yeah. It's not binary, it's good. It's a good lottery. I had roulette before, yeah. Good. He said Gaussian noise, let's say noise. For instance, in semiconductors, in Halbleitern, you know, on chips, you can use thermal noise, thermisches Rauschen. You know, there's some kind of thermal noise. Any other kind of, you know, what's sometimes if you use PGP encryption, some kind of encryption tool, you have to generate a key and they're asking for random numbers. Do you know how these encryption tools generate the original keys? Yeah? Mouse movement, exactly. You know, you look at the mouse movement and really, you know, they go down to the individual pixel and then they look which pixel you are touching in a certain time interval. And what besides mouse movement, does anyone else know? Yeah. Exactly, time between clicks. You know, they ask you type something. You type something and, you know, it's maybe one keystroke per second. And now if you measure it, but not with a second accuracy, Genauigkeit, but an accuracy of 1 microsecond, suddenly you get a lot of random variation between, you know, first key click, second key click, and so forth. So mouse movement, as in computer mouse, right? Yeah. Mouse movement, keystroke, timing. And there's pretty wild stuff out there. There was one random number generator in the 90s. I don't know whether it was a product, but people researched that. That was the spin velocity, so the frequency of the hard disk that spins, because there is some random variation by that, you know, to do air turbulences. There's radioactive decay, radioaktiver Zerfall, there's a certain randomness in that. So there's a whole bunch of random processes. Okay, so. And this is going to play a role in cryptography, but I just want to, for now, write that down this way. Okay, so this was the first type of random number generators, which is important in cryptography, not that important in this lecture, but in general, they are important in practice. They have the big drawbacks that they're truly random, and kind of part of this definition of being truly random is you cannot recreate them. What that means is, you know, you saw me with the €2 coin. If I do that 100 times, I don't want to do that because it takes whatever, 5 minutes. I'm slow with that. But I would start writing that down. You know, I would before had a 1 1 0 1 0 0 0 1 1 0 0 1. I'm making that up, okay? But that might happen if I do that 100 times, okay? Now, if I wanted to recreate the same sequence, it's virtually impossible, unless you're sitting here or you look at that video, right? But if I have 100 truly random bits, the next person who flips a coin 100 times gets a different sequence out, right? Everybody with me? I mean, that's the nature of being truly random. And that means in certain situation in cryptography, for instance, if you really want to create really unique private keys, you need this baby. Okay, you need somebody who's tossing coins, or probably you need keystroke timing or something. But in many other settings, we would like to have something that is random, but that can be recreated by somebody else. Okay, and in those situations, you need something that's somehow related to a pseudo-random number generators. Generators, or PRNGs. Again, very important abbreviation. Everybody's doing cryptography. If you tell that person, please give me a PRNG, they know what you're talking about, okay? Very important is, they're not really random number generators, that's why they have this P there, right? It's a pseudo. They're not real. They pretend to be, but they're not really, okay? Namely, truly random, we just discussed, they cannot be recreated. If I write 100 random bits down, it's really hard for anybody on planet Earth to come up with the same 100 bits. Pseudo-random numbers, the big thing is they're being computed. That means somebody else can do the same computation, okay? So pseudo-random numbers without the G, PRNs, are computed i.e., das heißt, i.e., they are deterministic. They're determiniert, so they're festgelegt. Okay, so they're not really random because you can compute them if you want. If you wish, it's the opposite of randomness. They're not really random, right? Because if you can compute something, it's not random, okay? Nevertheless, they have, as we will see later, from a different viewpoint, they behave like truly random numbers, okay? Often, they are computed with the following function, namely, your first random number is the seed value. This is coming from somewhere. Sometimes that is a truly random number, okay? Sometimes it's fixed, sometimes it's a true random number. And from now on, each subsequent Si plus 1 is a function f of the previous one, okay? Recursively being computed. So this is a very important thing. And towards the end of the lecture, we will see how this is being done. Or maybe we give you an example. Okay, I'll give you an example now. Example. The rand function in ANSI C. Okay, can I ask, do you already have the C lectures? You're already learning C, the programming language C? No, next semester. Okay, you will learn C. Okay, it turns out there's a programming language called C. You're learning Java right now, is that right? Java, okay. Before Java, there was C, and C is still very, very important, particularly in engineering. C has a random function, rand, okay? And this is specified, this is part of the official international standard. It's a rand function, and the rand function has a fixed seed, which is a nice value, 12,345, or 1, 2, 3, 4, 5. Okay, this integer value is part of the standard. That's the seed value. Okay, then the update function Si plus 1 is computed as, and now it's long, it's 110,351, 5245 Si plus this constant again, 1, 2, 3, 4, 5, and everything modulo 2 to the 31. Okay? So that's a pseudo-random number generator. It's part of the C standard. Okay, so this is a very common thing. Okay. So, and I'm jumping now a little bit ahead in the lecture. It's kind of tempting to use these pseudo-random number generators, something like, you know, the rand function at this point here. To use that to compute Si on the receiving side and Si on the transmitting side and the receiving side. It turns out that this is a really bad idea. This is crap. Don't do that. Okay? So you can't use the C function or most other PRNGs you cannot use in cryptography. Why? I'm going to explain to you in half an hour or so, right towards the end of the lecture. So what we need instead, we need pseudo-random number generators, but with a certain additional property, which only exists in cryptography, which are the third type. You know, we started with true random number generators, and we had pseudo-random number generators, and now comes the stuff we end up needing in cryptography at the end, which is being used in your cell phone, which is C, which are cryptographically secure PRNGs. It's a terrible long word, so that is the abbreviation is CPRNG. And most people don't know this abbreviation. There's actually only a few books use that. I use that in my books. A few other people use that in their books. Yeah, but it's not. But again, this is not heavily standardized. So if you feel happier with calling that CS for secure, please do that. Okay, there's no Punktabzug, you know. But it's I think I call that CPRNG in my book. Okay, so so what are there? They're essentially they're pseudo-random number generators. That means they're also deterministically, they're computed. They're also computed with some kind of update function, something like this here. It's very similar, but they have one property, namely CPRNGs are PRNGs. And if you don't understand one word, that's fine. Okay, it's really terrible what I'm doing. Okay, so cryptographically secure pseudo-random number generators, okay, are pseudo-random number generators, okay, with an additional property, also eine zusätzliche Eigenschaft, with an additional property, colon, Doppelpunkt heißt colon in English, Doppelpunkt, colon, the numbers are, and now everybody wake up, everybody don't do YouTube at this moment, okay, everybody's looking here, yeah, very good, they are unpredictable. You can go back to sleep. Okay. If you like color, that's the perfect time to use color in your lecture notes. Okay. What do we mean with unpredictable? The informal definition is given I give you n output bits, let's say n 1000. That means I give you 1000 bits Si plus 1 up to Si plus n minus 1. So I give you 1000 bits. Okay. And what happens then? And then it is computationally infeasible to construct SI. No, SN. You can copy that and then I'll discuss it a little bit with you. Okay. What that means, you have some kind of computer, some kind of algorithm, some kind of formula, some kind of function that computes for you, similar to what we have here, a function that computes all these S's, right? You get S1, S2, S3, up, blah, 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 up to S1000, okay? And I give you these S's, and now you as an attacker, your job is to compute S1001, okay? And if you cannot do that, that infeasible bedeutet unmöglich, unmachbar. So if you cannot do that with modern computers, or you have 10,000 Aldi PCs or something, you have a lot of computing power at your hand. If you cannot compute S1001, then this is unpredictable, computational secure. Okay? And why we need that, you will see that. Okay? And that's the informal definition. The full definition. Full definition is in section 2.2.1 of the textbook, right, of understanding cryptography. By the way, side remark, 30-second relax, the Fachschaft decided to buy all of you a textbook. It's your money, it's not my money, think yourself. So, okay. One thing which I want to tell you, which is a practical issue, this is not relevant for the exam, but terribly important for life as a cryptographer. There are many applications in life, in technical life, in engineering in particular, mathematics, where you need pseudo-random numbers. We need random numbers. Very often that means pseudo-random numbers. For software testing, for other test purposes, for all kind of application technology. In pretty much all cases, you're perfectly fine with number B, pseudo-random number generators. Okay? That means there's a rich body of literature. There's a lot of expertise, a lot of knowledge, a lot of understanding how to build good PRNGs with good statistical properties. But normally, they all are really bad for cryptography. And only in cryptography, you have this additional requirement of unpredictability, okay? That means if you ask general, let's say, really smart mathematician, give me a good random number generator for my stream cipher, they probably give you number B, a PRNG, a pseudo-random number generator, and they don't care about unpredictability, okay? And that in the history of cryptography, there have been a lot of really bad stream ciphers where they had a strong B, a PRNG, a pseudo-random number generator, but it wasn't very good with respect to unpredictability, and then you can throw that away, okay? So just be very, very careful if anybody tells you, well, this is a really good random number generator. Normally, they don't care about this because you need this only in crypto. All the other applications on planet Earth, you don't need unpredictability. So be careful, okay? That means, yeah. Ja, klar. This is. Do you have a cell phone? Yeah, so you have one. No, it turns out in cell phones, we have a random number generator here, and they're all unpredictable. It's exactly in your cell phone. If you get the first 1,000 bits from your cell phone out inside your cell phone, you cannot compute bit 1001. Very, very good question, but they do exist. Yeah. It's the A5 cipher suite. They're more or less secure. Okay. So this finishes chapter 2 of today's lecture. And now we come to a rather cool part of today's lecture. We talk about the one-time pad. It seems like a stupid random name, but it's actually a very, very, very cool cipher. So this is now number 3. Okay, so our goal at this point in the lecture is now we want to build the perfect encryption algorithm. Build a perfect cipher, okay? And perfect I put in quotation marks in Gänsefüßchen because we have to define what do we mean with perfect. Perfect, we mean, what would you say is perfect? When would you call the ideal cipher? The best cipher, yeah? Yeah. You cannot break it, you cannot brute force it. Informal, you cannot break it, right? This is now the informal definition. And now I give you a more formally one. That's a definition here, which is a little boring, like most definitions. A cipher is, quotation marks, unconditionally secure, end of quotation marks, unconditionally secure, uneingeschränkt sicher, in Klammern, or information theoretically secure. That was in Klammern, in parentheses. If it cannot be broken, even with infinite computing resources. That's another definition that's should be boxed in. Okay. So what we defined here is unconditional security, and another word for that is information theoretical security. But usually we're not using that, it's just that you've heard the term before. So we talk about an unconditional, we call a cipher unconditionally secure if it cannot be broken, even if we have many, many, many computers. This is what it says here. And what do you think is the most important word in this definition here? Which adjective is the most, yeah? Yeah, infinite. Okay. So for instance, if you tell me here's a block cipher with a key of 1,000 bits. To do a brute force attack, that would require 2 to the 1,000 operations. This is completely impossible. There are only about 2 to the, I think, 300 atoms in the universe. So you can't do 2 to the 1,000. This is way out. It will never be, mankind will never be able to do that, right? Well, according to this definition, is it secure? No, because infinite means infinite without end. So what I can assume is, okay, now I have 2 to the 1,000 computers. Each computer tests one key, and within one time step, within 1 second or so, I have the key. I know I cannot realize it because I cannot build 2 to the 1,000 computers, but still, it's not secure, according to this definition, okay? So what I'm trying to say, this is a very, very strong assumption. It means a lot of ciphers that are practically secure, key space of 2 to the 1,000, they are not unconditionally secure. So this is an extremely high requirement here, right? And now it turns out, and this is really cool, it's super, 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 super easy to build such a cipher. That means it's laughable easy. It's essentially on the blackboard there. It's extremely easy to build a cipher that has this unbelievably strong security requirements, okay? Wake up is an important part now. Definition. The one-time pad, also referred to as OTP, the OTP is a stream cipher where, and means with the property, but I'm just writing where, first property, the key stream bits SI stem from a TRNG. So the bits come from a true random number generator, and secondly, each key stream bit is used only once. That's it. And this should get at least 2 frames. This is very, very important. Okay. So, as my math professor said, auf der Zunge zergehen lassen. What does this mean? This is an unbelievable, it's very simple, it's an unbelievably strong statement. So what that means is, you take these type of ciphers that we, encryption is this really simple modulo 2, decryption is this really simple modulo 2, the key stream comes from your 2 euro piece. Okay, you take a 2 euro piece, or 1 euro piece, okay, whatever, yeah. I get some number here. I'm not telling you. Get a number here, I'm not telling you. You get the idea, do that 100 times, okay? Then I can encrypt my first 100 bits here, and the ciphertext, I get 100 ciphertext bits here, right? There is no way anybody in the world can break that, including our friends from the NSA, National Security Agency. You know, they're the biggest, allegedly, the biggest purchaser of computer hardware in the world. I mean, they have rooms like this full of supercomputers, right? Graphic cards, Cray, whatever, you know, Aldi computer, you know. Turnhallen voll Aldi computers, right? They cannot break that. Why is that? Well, for you, because of this definition. You cannot break that, okay? You cannot break that. Well, what does the receiver do? Well, the receiver has to know the sequence. You know, this 100 bits that I generated with my 2 euro piece, you have to somehow, you still have a key distribution problem, right? So the key has to be transmitted here. But if they know the key, they can decrypt, again, a very simple operation, and they get that out, okay? Extremely powerful, extremely simple, so it's great, okay? So if you really pay attention at this point, you should think, well, that was the 3rd week of Introduction Crypto. We got a perfectly secure cipher. It's really easy. We're done, right? See you next semester, right? You get the idea, right? We have something perfectly secure and it's simple. What else to learn? You know, what about the rest of the book here? Why don't we stop on page 25, right? You know, where's the catch? Where's the trick? So there must be, and there's a catch to it. What is, even though this is great because it's super secure, it's super simple, what is the one really stupid property of that? What is the drawback? Yeah. Very, very nicely. Big drawback. Key is as long as the message. Example, encryption of a 400 megabyte file. This is big, but it's not that big, you know. It's one illegal downloaded movie, right? You know, this is 400 MB, right? You get a CD from somebody. So, yeah, nobody does it. I know. So that means here, we're here, right? We're here in this picture, 400 megabytes, you know. Used to be a few hard disks, now it's a small fraction of a hard disk, right? So you want to encrypt that, what kind of key do you need? Well, every bit needs to be 1 bit for each byte here, so we have 8 times 400 MB. This is 3.2 gigabit of key material. Okay, this is a lot. It's really painful. And the problem is, first of all, it's really long. You have to distribute that to the right person, right? And the right person needs it. And then what is really tricky, you cannot reuse that. It's not that you give that person one big CD with, you know, 3.2 gigabyte of random, truly random data. You can do that. But then the next time you want to encrypt the video, you need fresh bits. Don't reuse that. Okay? There are really bad examples in the history of cryptography where people reuse that, right? So the Rosenthals, does anyone know the Rosenthals? The people that they were spies, alleged spies. I guess that's true. They were in the US and they leaked the secrets about how to build a Wasserstoffbombe, an H-bomb, to the USSR, to the KGB. And they allegedly they communicated with their spy master using one-time pads. You can do that also with letters. It's a very simple cipher, but they didn't have enough keys, so they started reusing the keys, and he got electrocuted. You know, he ended up in the electric chair. So don't reuse them. Okay, it's really scary. Okay. Okay. So, what do we do instead? And there will be a homework assignment. Actually, we talk about more. It's not just that the key is very long and cannot be reused. Now, if you play that through in your head, what happens is you say, okay, you really exchange a lot of keys. You know, you have a really big hard disk with random data, and you give to your partner. What's now happening is also, of course, you have this hard disk with random data. You must be really sure that nobody steals that data. You know, this one-time pad data, this SI bits, right? And what happens if you use them up? You cannot just throw that away. You must destroy the bits, because if somebody finds in your trash can the bits you used for encryption, they can still decrypt. So it's super complicated. It's not very nice, okay? And that means one-time pads and theory, a really great construct. In practice, I wouldn't say unusable, but they're very hard to use. And pretty much all commercial crypto products, PGP, other email encryption programs, file encryption, hard disk encryption, whatever, they don't use one-time pads because they're a pain to use. It's really complicated. There's some military application and some other very extreme applications where people use one-time pads, but not in normal commercial cryptography. So what they do instead, and that will be the last part of the lecture, the last 10 minutes, they use other type of random number generator. Essentially what we did at this point here, we said we took the first type of random number generator, namely 2 random number generators, and we tried to build a crypto system. It turns out it's really great if you do it right. You get something perfectly secure. It's quite impractical. Now we try the next thing. So this was, let's try A, let's try B. Okay? Now we try to build a stream cipher using B. Okay? So this is section number 4 of the class today. This is, and what we try is one specific PRNG, namely the linear congruential generator, also called LCG. Okay. The idea behind this, use a key stream SI. Again, so the whole lecture, everything we're doing here is how do we get the SI? So use a key stream SI. From a PRNG. Oh, that should be uppercase, sorry. So the idea is if you copy, leave a little space here, okay? The idea is, and you have to wake up, this diagram is very important, okay? The idea is, you put a PRNG in here, you put the identical one on the other side, you know, Bob gets also a PRNG. The PRNG generates the SI for you, the key stream here. And now the idea is, in order to prevent Oscar from generating the same key strip bit, the PRNG has a key. Okay? What you see here on the blackboard, this drawing, this is how all stream ciphers, practical modern stream ciphers work, this way. Okay? The only question is, what do we use at this point? So this is in your cell phone. Okay, this is a block diagram of keystream encryption with your cell phone. Okay. So, and one way of doing that is, what is an LCG? This is really, really simple. This is essentially, no, not essentially, this is already saw an example. Where was that? Here. The NZC function is an LCG. That means S0, S0 is the seed value. And this is uppercase, this is no Großbuchstaben. Okay, I switched to Großbuchstaben. You see, in 1 minute, you see why I'm using Großbuchstaben at this point here. So this is SI plus 1, this is uppercase S. Is some kind of constant times the previous value, Si, plus another constant, mod m, where all values involved, A, B, and the Si values are element of Zm or Zm. Okay. And the key K is comprised of the two values A and B. Okay. Okay, that's a key in the system. Okay. Clearly the key, and if you wish M, but I think for just to keep things simple, we assume that M is known, okay, to the attacker. Okay. And why do I use uppercase here? Because we're not operating mod 2, but mod m. But here this is still, you know, This is 1 bit here. You know, it's everything. We have 1 bit lines. This is everything is 1 bit here. So what we simply do is we compute more than 1 bit at a time. Maybe how many bits in this setting is remark A, B, and Si are log 2 binary logarithm of m. This is the bit length of m, okay? And then you do this Gaussian operator here. That means round it up, okay? We're going to talk about that in the Übung. Log m bits. What that means, if m is, for instance, a 30-bit numbers, A, S, and B are all 30 bits long. Okay, that's the basic idea. And what I want to show you now towards the end, and I hope you get that, and we're going to talk much more about it next week. All next week we'll deal with these type of attacks. So what we're doing is here we compute fresh symbols. So we start with S0, some kind of seed value, and then we compute S1, S2, S3, and each of the S's are maybe 16 bits or 32 bits, and then we have every time 32 bits that we can use here for bitwise XOR. What I'm going to show you, and it takes literally 2 minutes to break this baby here, okay? And this is not because this is a stupid random number generator. Is statistically speaking, with respect to randomness, you can get pretty nice results if A, B, and M are nicely chosen. You look on Wikipedia, you look in a good algorithm book, you look in Knuth's book on algorithms, you will find good values for A, B, and M. I can give you one set is here. This is A, this is B, this is M. Okay? You can do that, you get a really nice sequence out, very nice statistical property, cryptographically really bad. And now that takes 2 minutes to show you that this is really bad. How can we break that? Here's an attack. Attack goes as follows. We assume that Oscar knows 3 plain texts, x1, x2, x3. How would we know that? It's, for instance, there could be file header information. Or in the voice message encryption, there's sometimes some kind of protocol header. There might be the first few symbols, maybe the first, each of that is 31 bits, 31, 31, 31. That means the first 93 bits are known. This is very common. Have you ever looked in a Word file or an Excel file with an ASCII editor? There's all this, version number and other kind of junk of header information. So it's very, very common that an attacker knows the first few bits that are being encrypted. Okay? And here we only need 3 symbols that are being encrypted. Okay? And now, if he knows x1, he knows, the first 96 bits here. He also knows, of course, all ciphertext. Attacker, of course, has channel access, right? You must know the ciphertext. So what he can do now, he can just reverse this XOR operation. That means the attacker can compute SI here, okay? So first, Oscar computes S1, S2, S3, uppercase, Großbuchstaben. Okay. Okay, now we have 3. Now he has 3 outputs of the stream cipher, right? And why is that cool? Now you write the equation down. This equation, and remember, he wants to recover A and B. That's the key, right? The attacker doesn't know key, but he knows this equation, of course. It's Kharkov's principle, so the attacker knows that. So now what does Oscar do? Secondly, he writes the equation. Now, he knows S2 was computed as A times S1 plus B modulo M, right? And now you have to be mentally present for 2 more minutes, okay? So attacker knows S1, S2. What are the unknowns? Well, the unknowns are the key A and B, right? Okay. So how many unknowns are in this equation here? 2, obviously, right? A and B. And what type of equation is it? Does anyone know that? Is it a quadratic equation? Is it a cubic? Or is it a linear, right? Because A and B are in the erste Potenz, right? It's not A square or B cube or something, right? Okay, so this is A and B. So it's a linear equation, 2 unknowns, but you only have 1 equation. What does this mean? We cannot solve that. You cannot solve this equation for A and B. There are not infinite, but there are many solutions. There's no solution, okay? So what do we know? What do we need if you have a linear equation with 2 unknowns? How can we solve that? What's needed? Second equation, okay? What we want to have is 2 unknowns, 2 equations, linear, okay? Any ideas? Where do we get the second equation from? Any ideas? Exactly. This was the equation for, this was how S2 was computed. Let's see how the stream cipher computed S3. Well, S3 is computed as A times S2 plus B modulo M. And now the attacker won, and Alice and Bob lost. Now the system is broken. Why is that? This is a linear equation system with 2 unknowns. And my son Noah has been doing that since 8th grade. 8. Klasse, you do that in Nordrhein-Westfalen. So in 8th grade, he learned Additionsverfahren. And you too, okay? So what I'm saying here, this is super easy. 8th grade, you learn how to solve these babies, okay? This is not any kind of number theoretical, advanced, Gröbner Basen, blah, blah, blah stuff. No supercomputers. Paper and pencil, super easy, okay? So I give you the solution. A is S2 minus S3 times S1 minus S2 mod M, and B is S2 minus S1 parenthesis S2 minus S3 parenthesis closed, again times the inverse of S1 minus S2 mod M. Okay, it's really easy to break. That's in the lecture notes. You can copy that, but you'll find that this is in the book that you get soon. What that means is, if you use an LCG, linear congruential generator, here, this type of construction, if you observe 3 outputs, you can completely compute the LCG, and you know what's really bad about that? Now, we have A and B, and given A and B, we can compute not only S1, S2, S3, but S4, S5, S6, S7, S8, S9. Do you get the idea? From now on, Oscar can decrypt everything. So it's really bad. So don't use LCGs, and there will be many more homework problems on that. Thank you very much. Great lecture.